All right, welcome in everyone, kicking off another deep dive here. Today, we're going to dig into something that underpins, well, pretty much everything these days.
Yeah, it's everywhere but often invisible, right?
Exactly, we're talking about system verification. Basically, how do we know that the software running our lives, and I'm talking everything from cars and planes to, heck, maybe even your coffee maker, actually does what it's supposed to do, no big deal.
Yeah, supposed to do being the key phrase. Because as we all know, the more complex these systems get, even a tiny little error can spiral out of control. Consequences can be, well,
Let's just say high stakes.
yeah.
So no pressure on the software developers out there, right?
Great.
But seriously, where do we even begin with this? How do you actually make sure a piece of software, especially if it's controlling something critical, is truly, truly reliable?
You got to start with a healthy dose of reality, actually. Meaning we need to acknowledge that achieving absolute perfection, it's just not possible. The software industry, they even have benchmarks for this kind of thing. You might be surprised to learn that one common standard, it actually allows for one defect for every 1,000 lines of code.
1 in 1,000. Wow. Okay, my brain's already starting to hurt. Think about all the lines of code it takes to, I don't know, run a smartphone, let alone a self-driving car. No wonder verification is such a massive field.
Massive is an understatement. And to try and make sense of it all, we can think about it in two main categories. There's dynamic verification, and then there's static verification. Dynamic techniques, those involve actually running the software, putting it through its paces.
So kind of like setting up a crash test dummy, but for software. Laughs. Yeah, exactly. Testing, for example, is a perfect example of a dynamic technique. It's like we're throwing a bunch of different scenarios at the system, different inputs, seeing how it reacts, and making sure that what we get back, the outputs, match up with what we expect.
And simulation fits in here somewhere too, right?
Absolutely. Simulation, it's another dynamic technique. But instead of letting the actual software loose in the wild, so to speak, we build a kind of virtual model of it.
Yeah.
This is incredibly helpful when we're dealing with systems where real-world testing would be, well,
Way too risky or dangerous.
exactly. Think about like air traffic control software. Much better to have a simulated plane crash than a real one.
I'd say so. But even with all this testing, all this simulating, can we ever really be 100% certain that a piece of software is completely, totally bug-free? That is the million-dollar question, isn't it? And unfortunately, the short answer is no. We can't possibly anticipate every single scenario, every little quirk, every possible input that the real world might throw at our software.
It's like trying to plug every single hole in a dam, right? No matter how thorough you are, there's always that chance that you missed one, and even a tiny leak can.
Yeah, can bring the whole thing down. That's a rather dramatic analogy, but I like it. And that's precisely why, in addition to dynamic testing, we also turn to static verification techniques. It's about examining the software, sort of like the blueprints of that dam, before we even start building.
Okay, I'm intrigued. So static verification, you said it doesn't involve actually running the software.
Exactly. We're talking about examining the design, the actual code itself, without actually executing it. One common method we use is called static analysis, which can be done by software tools, kind of like imagine the superpowered spell checker for code.
Okay, so catching those pesky typos and errors before they can cause any real trouble. Makes sense.
Exactly. And it can be incredibly valuable. There was this case a few years back, a software bug that could have caused a rocket launch to go completely haywire. Luckily, static analysis tools, they caught the error during the design phase, saved millions of dollars, maybe even some lives.
Talk about high-stakes spell checking. So static analysis, it's like having a second set of eyes, or rather a computer program with some really, really good eyes, scrutinizing our code for anything suspicious. What other tools do we have at our disposal for this kind of static verification?
We've got review and inspection. Now, those might sound kind of simple, even old-fashioned, but they are surprisingly effective. We're talking about having expert reviewers, actual humans, comb through the code or those design documents, oftentimes using checklists of potential issues, looking for anything that seems off.
So it's like instead of checking for a typo, they're checking the logic itself, making sure the thought process is sound.
Yeah, exactly. And studies have shown that this manual review process, it can actually catch, on average, about 60% of errors.
Wow, 60%, that's impressive. But I'm guessing even with those really good eyes, it's not foolproof. Sadly, no. They're much better at catching individual errors. But when it comes to the more complex issues, those that emerge from how different parts of the software interact with each other, things can get tricky. For example, concurrency problems. That's where you've got multiple things happening at the same time and...
Things can get really messy really fast.
Exactly.
Okay, so for these really tangled, really intricate systems, especially when we're talking about, those life or death situations we mentioned earlier, are there any techniques that are particularly well suited to handle that kind of complexity?
There are, and they often go hand in hand with this static verification approach. Enter formal methods. This is where things get, I think, even more interesting. This is where we bring in the big guns of mathematics. We try to prove a system's correctness, not just test it. Okay, full disclosure, this is where my math-averse brain might start to check out. But please, do tell me more about these formal methods.
I like to think of it like this. Imagine instead of just testing to see if a bridge can hold weight, we're actually using physics and all sorts of advanced math to prove with certainty that that bridge is going to hold up no matter what you put on it.
Okay, so we're not just kicking the tires anymore. We're getting out the equations, the hardcore analysis. I like it.
Exactly. And one of the tools that we use to bring this kind of mathematical rigor to software is something called a labeled transition system, LTS for short.
All right, LTS. Sounds a little intimidating, not gonna lie. Is this where my math-phobic brain checks out?
Not at all. Actually, LTSs are surprisingly easy to visualize. Imagine a map. You got it. Okay, so we use this kind of graph-based system to represent all the different states that our software can be in, kind of like locations on that map.
Okay, I'm picturing a map. So each point on the map, that's like a different snapshot of what our software could be doing at any given time.
Precisely. So let's stick with your coffee maker example. One state might be waiting for input, right? Another could be brewing coffee. Another could be completely out of water, flashing red, help. You get the idea. And then the transitions, those are the lines connecting those states on our map, they show us how the system can move from one state to another.
So the LTS, it's like it helps us map out every possible thing our system could be doing and how all of those actions are connected to each other.
That's the gist of it. And the really cool thing is that we can use this map, this LTS, to start proving things about our system. We don't have to check every single possible scenario individually.
Now that you mention it, that sounds especially useful when we're talking about these super complex systems where the number of possible scenarios could be, well, almost infinite.
You're talking about the state explosion problem. It's a real challenge, but it's not insurmountable. Remember those transitions, the lines connecting our states? Well, by analyzing those connections and making sure that they follow certain rules, we can often prove something about a whole section of our map without having to visit every single point individually.
So it's kind of like we're checking the logic of the system, the underlying rules that govern how it moves from one state to another, rather than getting bogged down in every single possibility.
Exactly. And a key concept here is something called an invariant. It sounds like something out of a superhero movie, but really, an invariant is just a property that always holds true no matter what transitions occur. Think of it like a law of physics for our system.
Okay, so if we can prove that these invariants always hold true, then we can be more confident about a much larger portion of our system without having to check every nook and cranny. That's incredibly efficient.
Exactly. That's one of the big reasons why LTSs are so powerful. Of course, no tool is perfect, and there are limits to how much complexity even the most sophisticated techniques can handle.
I was just going to ask, are there ever situations where LTSs just, I don't know, hit their limit, they can't quite grasp the complexity?
For sure. For extremely complex systems, even with all the clever techniques, the number of states and transitions can just become completely overwhelming.
Yeah.
And of course, the effectiveness of an LTS, it depends on how well the system was modeled in the first place. If the map is inaccurate or incomplete, our analysis isn't going to be very helpful.
Right, garbage in, garbage out. So it sounds like even with these really cool tools, there's still an element of human judgment involved.
Always.
Yeah.
Actually, in the real world, system verification, it's almost never about relying on just one technique. We often use what we call a multi-layered approach. Dynamic testing, static analysis, formal methods with those LTSs, good old-fashioned human review, all of that together helps us build a more robust picture of how reliable a system really is.
So it's about using the right tool for the right job and also understanding that there's no magic bullet, right? No single solution that's going to guarantee 100% error-free software every single time.
Exactly. It's a constant process, improvement, refinement, especially when we're talking about these safety-critical systems where the stakes are so high.
You mentioned earlier that formal methods, they're especially well suited for those high-stakes situations. Can you walk us through, how formal methods, especially combined with these LTSs, how they give us that extra level of assurance that things aren't going to go, well, catastrophically wrong.
Absolutely. Remember, with formal methods, we're not just testing to see if a system behaves correctly in a bunch of different scenarios. We're actually using mathematical logic to try and prove that the system must behave correctly, at least under its intended operating conditions.
So it's like the difference between, I don't know, glancing at a bridge and being like, yeah, that looks pretty sturdy, versus having an engineer come out and do all the calculations and say, yep, this bridge can handle this much weight, no problem.
That's a great analogy. And LTSs, they provide that structured framework for applying those formal methods. We take our system design, we translate it into that graph-based representation, the states, the transitions, remember. And then we can start expressing the desired properties of the system using something called temporal logic.
Temporal logic. Okay, now that sounds like we're getting really deep into the weeds here.
It's not as complicated as it sounds. Really, think of temporal logic as just a way to write mathematical statements about what should or should not happen as the system moves from one state to another. We're basically writing the rules that our system has to follow, always, no exceptions. It's like setting boundaries on that map we were picturing.
So instead of just saying this button should make the coffee brew, we're saying it is always the case that if the coffee machine is in the idle state and the brew button is pressed, it will then and only then transition to the brewing coffee state. We're being super precise.
Exactly. No room for ambiguity here. And this is where things get really cool. Once we have our system model in that LTS form, and we've got those desired properties expressed in this nice formal temporal logic, we can actually unleash these really powerful automated reasoning tools to check if those properties hold true for every single possible path through our LTS.
Okay, now you've got my attention. Automated reasoning tools. What are those?
Think of them like superpowered mathematical assistants. They go through our LTS, following every possible route, every possible scenario, making absolutely sure that our mathematically defined rules are never, ever broken.
So it's like having a computer program double-checking our logic, making sure that we haven't missed any sneaky loopholes or contradictions.
Exactly. And the really cool part, if those tools find even the tiniest possibility of our rules being violated, even in some obscure edge case that we might never have thought of, they'll flag it. They can even often provide what we call a counterexample, a specific sequence of events that leads to the problem. So it's not just, hey, you messed up. It's like, hey, you messed up, and here's exactly how.
That is super helpful. It's not just about finding errors, it's about understanding why they might occur. So it seems like this combination of formal methods, these LTSs, it gives us this amazing level of scrutiny that we just couldn't achieve with like traditional testing alone.
That's the idea. It's about moving away from this test and see approach to more of a prove it correct mindset. And while, again, no system is perfect, this level of rigor, it's absolutely essential for those systems where failure just isn't an option. Think about the software controlling a medical implant or a self-driving car. We need to be as close to certain as we can possibly be that it's going to do what it's supposed to do.
Absolutely. But I imagine this level of like mathematical certainty, it's got to come with its own set of challenges, right? What are some of the hurdles in actually applying these formal methods and these LTSs in the real world?
You're right, it's not always easy. Expressing these complex systems and their desired properties in this really rigorous mathematical language can be a real challenge, very time-consuming. It often requires very, very specialized expertise, which, let's face it, not every development team has just lying around.
So there's definitely a learning curve there, maybe even a resource constraint for some teams.
Sure. And then there's also the issue of scale. As systems become even more complex, even with LTSs and other cool techniques, the sheer number of states and transitions, it can still be just overwhelming. Even for those automated reasoning tools, it's a constant balancing act.
So there's still a practical limit to how much we can formally verify, even with these amazing tools.
For now, yes. But that's what's so exciting about this field. Research, informal methods, automated reasoning, it's always moving forward. New tools and techniques are being developed all the time to handle even larger, even more complex systems.
It's like a race, almost, between the increasing complexity of the systems we're building and the tools that we're using to make sure that they're actually correct.
And it's a race with incredibly high stakes. But the good news is that even making a little bit of progress, that has the potential to make a huge difference in the safety and reliability of the technology that we all rely on every single day.
Speaking of increasingly complex systems, It's kind of wild to think about just how much, well, everything around us depends on software these days. I mean, we've got self-driving cars, AI that's being used in medicine, everything's connected. Seems like we're always pushing the limits, making things even more complex.
It's true, and that's exactly what makes this whole, race for better and better verification tools so important. Because it's not even just about the complexity of one system anymore, right? It's about how all these complex systems, they interact with each other.
Yeah, it's like that butterfly flapping its wings thing, right? Like a tiny bug in one system somewhere, who knows? It could create chaos in ways we never even thought about. So how do we even approach that? I mean, are there verification techniques that look at these bigger picture interconnected systems?
That's where things get really, really interesting. Researchers, they're developing techniques right now that analyze not just one component in isolation, but the overall behavior of these giant systems of systems.
Okay, now you're blowing my mind a little bit. So instead of just verifying if, say, a self-driving car's braking system works by itself, we're trying to figure out how that braking system interacts with other cars, traffic lights, pedestrians, the whole shebang.
You got it. It's about understanding something called emergent behavior. Basically, those unexpected outcomes that happen because all these individual components, they're all doing their own thing, but they're also interacting in this, complex dance. So it's not enough to just make sure each part works on its own. It's got to be about making sure that the whole orchestra is playing in tune, if that makes sense.
Makes perfect sense. So it's like we're not just debugging code anymore, we're debugging the entire system, the way everything works together. That is a whole other level. Are there like specific approaches for tackling something that big, that interconnected?
There are some really cool things in development. One that's showing a lot of promise is something called runtime verification. So a lot of the traditional verification stuff we talked about, that happens before you even release the software. But with runtime verification, what we're doing is we're constantly monitoring the system as it's running, looking for anything that seems off, anything that doesn't match what we expect to see.
So it's like we're giving this software a self-checkup. It's like it's got its own little doctor inside, constantly running tests, trying to catch those problems before they become major issues.
Right.
It's a little bit like that.
Sure.
And it's becoming more and more important as these systems just get more complex. These runtime verification tools, they use sensors, logs, data streams, everything they can get their hands on, basically, to keep an eye on things. And if they see something that looks even a little bit suspicious, they can send out alerts, isolate the part that's acting up, even start some automatic recovery procedures to try and fix things on the fly.
So it's not just about finding those errors anymore. It's about building these systems that can adapt, that can heal themselves. Wow, that is incredible.
It's a super exciting area of research, and I think it really highlights how system verification, it's evolving. It's about more than just, is this correct? It's about creating these resilient, adaptable systems that can handle curveballs, that can even learn and get better over time.
This whole deep dive has been amazing, really eye-opening. We started with code analysis, dove into formal methods, and now we're talking about these self-healing systems. It feels like we're on the verge of something completely new, a whole new era for how we build software.
We are, and in this new era, the ideas behind system verification, they're going to be more important than ever. Software's everywhere, transportation, healthcare, finance, you name it. The stakes are higher than they've ever been.
You're right. And we've talked a lot about the technical stuff, but there's obviously a human side to all this too, right?
100%. Even with the most amazing verification tools in the world, they're only as good as the people using them. The ones who are designing, implementing, interpreting those results, building these really reliable systems, it's about more than just tools. It requires this whole culture of thinking carefully, testing rigorously, and being open to new ideas as technology changes.
So it's about the mindset as much as it is about the tools themselves. It's a really important thing to remember for anyone who's building the technology of the future.
I couldn't agree more.
Well, I think we have given our listeners a lot to think about today. From the limits of verification to these new possibilities like runtime verification, it's clear that this journey towards more reliable, more trustworthy software, it's ongoing, it's constantly evolving.
And it's a journey that requires both of those things you mentioned. Brilliance and a sense of responsibility, for sure.
Absolutely. So to everyone listening, as you go about your day, think about all the hidden efforts of the people working behind the scenes to make sure that the systems we depend on, that they're as safe and reliable as they can be. Because in this world, a world that runs on code, verification, it's not just a technical problem to solve, it's a shared responsibility for all of us.
Well said.
That is a fantastic point to wrap up on. Thanks for joining me on this deep dive. It was fantastic. And to all our listeners out there, until next time, Stay curious.